Abby's TV. Did you see that? In the Slack? We're here to be live, but we're all here. Okay.
As in, like mute or leave?
Great. One of you. It's fine. Our mic. Our mic's hot. Someone who is there, please tell me if my mic is hot.
audio capture. Sorry.
Ah, we're on. It's hard to tell. Hello, everyone. Thank you all for coming to our first ever virtual Astronomy on Tap for Baton Rouge. We're very happy to have you guys here. We've been missing having Astronomy on Tap during all this downtime that we've been having. So as we go on, just a couple ground rules that I want to lay down. So bear with us. Of course, this is our first virtual show. If anything goes wrong, we're very sorry. We are not versed in streaming on YouTube at all, but we're gonna give it a good try, and hopefully it works out well. And feel free to leave us any feedback whenever we're done if there's any comments that you have. During the talks, feel free to comment any questions you have in the chat. You can ask them at any point during the talk. We have a couple people watching the chat, and we'll make sure that we get most of your questions. Please don't spam the chat. We can time you out. So if that becomes a problem, then we may have to time you out. So just ask the question once and we will most likely read it. Please feel free, or please consider donating to our Venmo and PayPal. Of course, we can't have our tip war or our tip jars like we normally do, but we do still have a tip war. This month, we're asking you, which Mars rover do you prefer as a battle bot? And we have two different options. We've got Perseverance, who's armed with a hammer and a laser, and we've got Curiosity, who's armed with a flamethrower and 2 spinny arms. So if you do make a donation, please just in the comment, let us know which one you vote for, and we'll let you know who wins at a later time. So up first, we have our first talk from Matt Penny. He is a professor here at LSU. He did his postdoc at Ohio State University, and he's Welsh. He's got a really great Welsh accent. So hopefully you get to see his black cat. Otherwise, say hi to Sylvia in the chat. But we've got Matt Penny, and if he wants to share his screen, we can get going.
Hi, everyone. It's good to be here virtually, if not in person. So as Courtney said, I'm Matthew Penny. I'm an assistant professor here at LSU, and I'm going to talk today about visitors from outer space. So not ET, the extraterrestrial, but instead interstellar asteroids, comets, and rogue planets. So first, before we start, we should probably discuss what exactly we mean. What's an asteroid? What's a comet? And I'll get to rogue planets at the end. So asteroids, they range in size from anything from boulders up to even mini planets. So the largest asteroid series is a spherical world that looks just like a planet. And when it was discovered, it was thought to be one. Only later were more and more asteroids discovered, and then it was downgraded to a new class of object. Most of the asteroids we know of live between Mars and Jupiter in the asteroid belt, but there's also a population of objects beyond Neptune, the Kuiper belt objects, one of which is Pluto, again, initially thought to be a planet, but there are a lot more things like it in roughly the same place. They have a variety of compositions, so some are rocky, some are icy, and some are purely metallic, so almost pure iron or nickel. The comets aren't that different. They're not as rocky. They're mostly made of ice, a combination of ice and rock. But the main difference is that they spend most of their time at very large distances from the sun. But occasionally, one of them will fall in towards the inner solar system, and as it comes closer to the sun, it warms up. The ices and the volatile material on it will heat up and vaporize, and that will cause it to have a long tail of gas and dust that streams away from it, away from the sun. So basically, comets are quite similar to asteroids, other than that they're almost always icy, and they've essentially fallen out of the deep freeze into the warmer inner parts of the solar system. Some of them might be periodic, like Halley's comet, that comes back every 86 years or so. But others fall into the solar system once and then leave, never to be seen again, or not to be seen again by humans on any kind of timescale. Some have orbits of hundreds of thousands of years, millions of years, and some just don't come back at all. So where do comets and asteroids come from? They're basically the leftover building blocks of the solar system. So the solar system and the planets in it, Jupiter and the Earth that we live on, all formed from the same disk of gas and dust that formed around the young sun. In that disk, dust stuck together, formed larger and larger objects, building up from pebbles to rocks to mountains to planets. And in that process, some of those objects just didn't grow as much as others. So we're left, in addition to the planets that did form, we're left with lots and lots of asteroids and comets, all scattered all over the place. Astronomers have been searching for these for a long time. Ceres was discovered in 1801, and ever since, people have been looking for more of them. We now know of nearly 1 million asteroids. I bet that number might have already ticked over the 1 million mark by now. And also we know of over 3,000 comets. These have been found with a range of telescopes, from ground-based telescopes that are dedicated to searches to just random discoveries. And many of the known asteroids of comets that have been discovered in the past by amateurs. So people just looking for new objects that move in the sky. Within the last few years, NASA has started using an old spacecraft to look for them too. The WISE spacecraft, and the mission is now called NEOWISE. So it was just another normal night at a telescope that searches for asteroids. 19th of October, 2017, the Pan-STARRS telescope in Hawaii was searching the sky, as it always does, looking for new objects. And one of the objects it found appeared as a streak in a single image that it took. This is shown here. And other than being a bit longer than a regular asteroid streak, it looked just like any other asteroid. But with follow-up observations that were taken over the next few nights, this asteroid quickly became clear that this was no normal asteroid. In particular, it was a really fast asteroid. So it turns out the solar system had a speed limit. The speed limit is set by where you are in the solar system. Just like in a city, you can't go as fast as you can out in the countryside. In the solar system, any object that's bound to the sun must obey that speed limit. So if you have an object near the Earth, it's limited to going a speed of 42 kilometers per second. Not miles per hour, kilometers per second. So much, much faster than we're used to traveling on Earth. And the Earth itself goes 30 kilometers per second, but if you dropped an object from the very far reaches of the solar system and just let it accelerate under the sun's gravity, the fastest it could possibly go is 42 kilometers per second. But this new asteroid that Pan-STARRS found was traveling faster than that. It was going nearly 50 kilometers per second, which meant that although it could possibly have been disturbed by an encounter with a planet, if it hadn't, then it must have come from outside the solar system and have been traveling at a greater speed than anything that's bound to the sun. At its closest approach, it reached nearly 90 kilometers per second. So after enough observations had been gathered, astronomers could calculate its orbit around the sun based on the amount that the sun caused its path to bend, and indeed it was seen to be an interstellar comet, so an interstellar object, something that had come from outside the solar system. So even though things inside the solar system may have very elongated orbits, this one had an almost radial orbit, so it's almost a straight line directly at the sun, and moving faster than any comet that had been seen before. So where did it come from? It turns out it came from a point in the sky very close to what's known as the solar apex. So this is the point in the sky where the sun is moving towards relative to the nearby stars. So if this thing was an interstellar object, this is precisely where you'd expect to see it come from. It's the region of space that the sun is moving towards, and so that means that any objects just drifting around in space would appear to come from that direction. And so over the course of 2017, it took a path through the sky, and then after its close approach to the sun, got whipped around and sent back in relatively close to the same direction. Astronomers didn't just look at where it was, but they also measured how bright it was. And this was a really weird part of something really weird about this object. So over just the course of a few hours, the asteroid appeared to change in brightness by a factor of almost 10. And so what this means is that if it's only reflected light that's coming from it, it must change in size or projected size by a factor of almost 10 as well. And this happened over the course of roughly an hour, going from brightest to faintest. If this was close enough to see with the naked eye, it would have been like going from the brightest star in the sky that you can see from Baton Rouge to almost the faintest that you can see through our light pollution. So that's a really dramatic change. And it turns out that models of the exact behavior of this pattern of brightness over time showed that the asteroid was indeed elongated, probably about 1,000 meters long, maybe not quite that big, but of order a kilometer long and roughly 10 times smaller on the small axis, so kind of cigar shaped. And a detailed modeling of this changing brightness showed that it's not just rotating, but it's tumbling, kind of like a tennis racket if you throw it in the wrong way. So pretty chaotic motion. So what was this object called? It needed a new naming system as something that had come from outside the solar system. So now it's an object with a new numbering and name system. So it's called 1I, and then its name, it was chosen to be Oumuamua by the discoverers. So the discoverers were based in Hawaii, and they sought native Hawaiian voices to pick a good, appropriate name for this object. And in native Hawaiian, it means scout or messenger from the distant past reaching out to us. The name was chosen by a Hawaiian navigator and a Hawaiian linguist, so particularly well chosen. It's the first interstellar asteroid, so it has the designation 1I. As I said, it's elongated and tumbling with a scale that long axis about a kilometer, short axis about 100 meters, about the length of a football field. It's got many strange things about it. First, it's strange that it's not a comet. So most of the material we expect to see ejected from solar systems is the stuff at the very edges. That tends to be icy, and so on its first approach through our solar system, we would have expected it to heat up and then vent gas just like comets do, but it didn't. Another strange thing, on its way out of the solar system, it appeared to accelerate a little bit. Very tiny amount, but a detectable measurement. That could have been caused by just a tiny amount of outgassing, but it's still quite enigmatic. So we have this elongated object moving through the solar system from outer space, and it starts accelerating. Sounds almost like a spaceship. So astronomers checked for this. So if it were an alien spaceship, it might be expected to be emitting radio signals. So astronomers use the Green Bank telescope through the Breakthrough Listen project to point at Oumuamua and search for radio signals. they would have been able to detect the radio signal from a cell phone, even at the great distance that it was at, but they found nothing. So it looks like it wasn't intelligent alien visitors, just a rock that was traveling through space that we expect to be traveling through. We've just been unlucky in our searches for them so far. But these things are like, it's like a bus. So you wait for 50 years after a prediction, but you can have interstellar asteroids and comets pass through the solar system, none arrives, and then 2 arrive in a couple of years. So pictured here is Gennady Borisov, a Crimean amateur astronomer with a telescope he built. And almost a year ago, in October 2019, he discovered a new comet with this bucket-like telescope that he has. He noticed it was moving really quickly, so he reported it to the authorities at Harvard, the Minor Planet Center, who helped to arrange follow-up observations. And again, this thing moving quickly is another sign that it might be an interstellar object. Or it might be an object that's very close to the Earth and has a danger of hitting us. Thankfully, in this case, it turned out to be another interstellar object. So this one is now called 2I Borisov. Being a comet, it has a slightly different naming procedure, and so it's named after the discoverer. This object came from basically above the solar system and traveled to about the distance that Mars is from the sun, and then got turned around, not quite as extremely as Oumuamua, and has been making its way out of the solar system for the past year. It's just about now reaching the point where it's not possible to detect it even with the largest telescopes. But thankfully, in this case, we saw it much earlier than we did Oumuamua. Oumuamua was on its way out of the solar system before it was discovered. Borisov was discovered on the way in, so astronomers have had about a year to study it. And in addition, it's a comet, not an asteroid, so it's being nice and helpful and throwing out its insides, all its gases and volatile elements. So we can study with spectroscopy, basically splitting its light up into all the colors of the rainbow. We can study its chemical structure through unique fingerprints they leave on that pattern of colors. And so with this, we astronomers have found a number of elements, including cyanide, carbon monoxide, not great elements, but elements that are relatively simple, not great for humans, but they're simple molecules that form in space. They've also seen water, oxygen, and other molecules. These things are things that we see in regular solar system comets all the time. But what's interesting about this one is that it has a lot more carbon monoxide than almost all the comets we've seen so far. Only a very small number with more. This is what gives it its interesting blue hue in this picture here from the Hubble Space Telescope. And just so I'm clear here, this picture of the Earth here is the size of the Earth as it would be seen at the same distance. So the amount of gas that it throws off, it might not be a very large amount, but it spreads out and it makes it very easy to see when it reflects sunlight. Not just gas, but dust as well. It's the dust that we're seeing reflecting light. So it's this chemical composition that it has can maybe give us a clue about where it came from. So if it's rich in carbon monoxide, this isn't a molecule that's very easy to break apart with heat. And so it seems to be a comet that formed around in a very, very cold place. And in particular, it might be from a comet that was formed around a red dwarf star. On its way through the solar system, it gave us a bit of a fright. It seemed to break up back in March of this year, although after only a few days, it was even after, so its nucleus appeared to split, but after a few days more in April, the comet survived and could still be observed. So now it's thought that that event was not a breakup en masse of the comet, but instead just maybe a boulder or something small breaking off and releasing a large amount of gas. If we trace back its orbit, it came from a different location than Oumuamua did. And some astronomers in Poland have done the calculations to trace back its orbit along its path and look at the motions of nearby stars to see if it came from any one of them. And it turns out that millions of years ago, Borisov would have passed, or would have been roughly 5 or 6 light years from the star Kruger 60. This is a nearby pair of red dwarfs that are so close that we can see them orbit over time. And at the time that Borisov would have been near them, they would have been traveling at very, very similar speeds. There's still a huge amount of uncertainty about this. There's still more orbital data needed to improve the calculations, but it's an intriguing target, and it would match with the chemistry of the comet. So we've seen 2 interstellar objects pass by the solar system in 2 years now. Are we going to see more? The likelihood is yes. So astronomers have gradually been improving their instruments and technology to be able to survey larger portions of the sky to see fainter objects over time. And in particular, in the next few years, the Vera Rubin Observatory in Chile will come online and will expand humanity's ability to see dangerous asteroids and faint objects by a significant margin. And so this will find many, many more asteroids than are known currently. And hopefully we'll find many more interstellar objects too. Another question we can ask, though, is, well, these are small objects. What about larger objects? If asteroids and comets can be thrown out of their solar systems, can planets be thrown out? And if you have a close enough interaction between 2 planets in a star system, then indeed they can throw out a planet. So we hope that one of those won't come and visit the solar system. That would be bad for everyone and all the planets in the solar system. But we can search for them before they get here, or even if they are not going to pass anywhere near us. So we do it in a slightly different way. Rather than looking for light from the planet itself, we can watch for a planet, an interstellar planet or a rogue planet passing in front of another star. And rather than blocking the light of that background star, the mass of the planet will in fact bend the light around it and cause the background star to get brighter. This is a phenomena known as gravitational microlensing. We've been using it for the past 20 years or so to search for planets around other stars, but if anything has mass like a rogue planet floating on its own, that too will cause a microlensing event. And in recent years, we found a few very, very good candidates for this. So the plot I'm showing here on the middle right is the brightness of a star over time. And this star in particular brightened in a pattern, my apologies, the cat is moving the camera, in a pattern reminiscent of a microlensing event caused by a low mass object, in this case, an object the mass of Neptune. And in the future, this is one of the things that I work on closely, and a study that was led by a graduate student at Ohio State, where I was, Samson Johnson, has shown that with an upcoming NASA telescope, the Nancy Grace Roman Space Telescope, which is a wide field version of the Hubble Space Telescope, basically can image 100 times the area that Hubble can. This telescope and the surveys it will conduct will allow us to find hundreds of rogue planets. with masses ranging from Jupiter down to things as low as Mars, Mercury, and even as low as Pluto if there are enough such free-floating objects out there. So the future is bright, even though we can't see these things. We're hoping to learn a lot more about them. And with that, I will stop and say thank you for listening and answer any questions you have.
Matt, if you want to pull your screen down, we can get started with the Q&A. Since I am the MC, I have the honor of asking the first question, of course. So I wanted to ask you, there was a big a story that got aired on some media websites very recently that was about an asteroid that was going to run into the Earth before the election day. Do you have any comments on that?
So I know very little about this asteroid, but I have seen the news stories as well. So from what I understand, this is first a very small asteroid, only about a meter across. So those kinds of asteroids can hit the Earth and will burn up in the atmosphere, and they may cause an explosion, but it would not be a significantly damaging one. It would be an explosion high up in the atmosphere. It might break some glass, but that's probably the worst of it. And then the other thing is I believe in this case, the being such a small asteroid that it was only seen over a very small range of time back in 2018, and so its orbit is quite uncertain. So there's only I think a 0.4% chance of the asteroid hitting us. There's just too much uncertainty in the measurements as yet, and until it comes back, we're not going to be able to see it and get a better guess of where it will pass.
Yeah, I feel like we should make a habit of if you're reading an article and an astronomer didn't tell you about it, it's probably accessorized a little bit. We have a question from Susan Dorsher. She says, what actually is the chance of a rogue exo-Jupiter, and what would it do to the solar system?
Oh, that's a good question. So with the current microlensing surveys, we now have some pretty good limits on the number of such rogue Jupiters there are. So there's less than one, it's about less than one rogue Jupiter for every 4 stars. So that's very few. And so there's actually a greater chance of a star passing through the solar system than there is of a rogue Jupiter, which again, that would be pretty devastating as well. And it hasn't happened because otherwise we wouldn't be here. What would happen? It really depends how close it got to the sun and to the planets. If it, I'm sure it would adjust so something the mass of Jupiter would almost certainly tweak all of the planet's orbits in the solar system if it came within the same kind of distance that Jupiter does of the planets now. And the trouble is with orbits, they're chaotic. So if you even displace the planet's orbits by a meter in the millions of kilometers that they currently are, and run a simulation forward for where you expect the planets to be, the outcome will be completely different. So some planets could get ejected from the solar system, some could crash into the sun. It's not something we would like to take our chances with.
All right. Allie has a question from one of her friends, and she wants to know, are you team Pluto is a planet or not a planet?
I'm team Pluto isn't a planet. It's very small. It's in a region of the solar system where there are objects very similar to it in very similar orbits. If we included Pluto as a as a main planet. I should say Pluto is a dwarf planet. I'm happy to call it a dwarf planet. So it's a planet in that sense, but it's a very different class of object to the rest of the planets. And there's tens, maybe 30 or so similar objects that we know of. So if you include Pluto, you've got to include all those other dwarf planets too.
I had another question. So a lot of people probably got out to see Comet Neowise if they had a nice pair of binoculars. Was there anything cool about that comet, or was it just pretty standard?
It was cool because it was bright. I don't know. I managed to find it in binoculars from close to downtown Baton Rouge, and it was a little disappointing. But it was certainly visible. But if I hadn't have seen it move between nights, I wouldn't have been sure I'd seen it. So it wasn't quite the spectacular show that we were looking for. To be honest, I'm not too familiar with Neowise itself. I don't know whether it was special or not.
Fair enough. Tom Morrill asks, has a rogue star been found anywhere near our solar system, or just in general?
So I can't get feedback on what you mean by a rogue star easily. So I'll try and guess what I mean by what you mean by your question. So a rogue, well, stars for the most part are just floating through the galaxy by themselves anyway. So there's, so I guess what you mean is a star or a planet that's dark and hasn't been seen. So there's certainly a very good chance that there are still very small objects that haven't been seen because they're so dark. But I think at this point we will have been able to see every star that exists. So everything that's glowing from either nuclear fusion or is still glowing from just the formation. So things that didn't quite make it to stars, so brown dwarfs, that are more massive than Jupiter, but are not burning hydrogen through nuclear reactions in their core. Most of those within the very close distances to the sun will have been found by now through infrared telescopes. But planets the size of probably a few times the mass of Jupiter, certainly on down, we would not have been able to have seen with any method that we have, unless they happened to pass in front of another star while we were watching.
Very nice. I'll give everyone just like a few more seconds to see if they have any questions. Since we have a bit of a delay, it may take a few more seconds. I'm trying to monitor and make sure my cat doesn't start screaming as well. So, because that wouldn't be very fun for everyone. Okay, well, if we don't have anything else, if they do, they can feel free to ask more questions. Feel free to type them out, and we can bring you back on at the end and ask them to you then. How's that?
Happy to.
All right. So with that, we're going to go ahead and take a quick break. It's going to be about 5 minutes. All we're going to do is, switch over to our new speakers, give everyone a chance to go and, use the bathroom, make themselves a drink, anything like that. And we'll be back in just about 5 minutes. While we're gone, feel free to donate to our Venmo or our PayPal. Let us know which of your battle bots is your favorite, Percy or Curiosity.
Yeah, the backgrounds are not ready for that.
All right, everyone, we are back here with our second speaker, Patrick. I'll go ahead and introduce him, but you've already got his slides up. He's talking about TESS and how it is certainly not a telescope for exoplanets. He is also a friend of mine from my undergraduate. He's a graduate student right now at The Ohio State University. He's a huge sports fan, especially football. He's an NSF graduate research fellow, and the best part, he has a bad habit of drunkenly buying big cat textbooks. This is Patrick Vallely, and he'll be talking to us about TESS.
All right. Yeah, thanks, Courtney. So today I'm going to be talking a little about TESS, but just, yeah, Courtney covered most of this, but I just want to mention that at Ohio State, I work on the all-sky automated survey for supernovae. So this is called a TESS, and it's a global network of small telescopes that monitors the sky. We try to get an image of the entire sky that's not behind the sun every night. For basically, we're searching for new supernovae and other transients, or just things that weren't there yesterday that are there today. Events, and my focus is on leveraging Assassin to discover new events in the TESS field of view and be able to study them once we get that TESS data down, which takes a minute because TESS, requires processing of their data. But yeah, like Courtney said, I love football, love a lot of sports. It's a good time. So what is TESS? I imagine some of you here are probably familiar with exoplanets. You may have heard of TESS, but for those that aren't, TESS is the Transiting Exoplanet Survey Satellite. It was launched just a few years ago. It's pretty young by NASA mission standards, and its primary goal is to find exoplanets by surveying all the nearest stars to look for these transit events. So when I say transit events, what I mean is kind of shown in the upper corner here. You can see, and it's pretty easy to understand. If you have a planet pass in front of the star, the brightness of that star is going to dip a little bit. It's not a lot. A planet is smaller than a star, and you're a good ways away from the star. But if you have a really sensitive instrument like TESS, you're able to see that little dip. And if you see several orbits where the planet dips, you're able to say, aha, that's probably a planet. Let's go look at it with something else, confirm that it's a planet, and then we can do some great science with it. TESS is a successor to Kepler in a lot of ways. So Kepler was another mission that was looking for these transit signatures for exoplanets. But TESS is a bit different from Kepler in the sense that Kepler looked at a pretty small patch of the sky, and it stared there for a little over 4 years. Whereas what TESS is trying to do is survey all the really nearby bright stars. And so to do that, it's trying to cover the entire sky with about a month worth of data throughout all of it before moving on. So the way TESS observations work, it's a pretty neat novel satellite, is it takes these 4 really wide field of view cameras, it puts them in a line, and it stares at a given spot. And while it's staring, it's taking images every half hour, which is an extremely good cadence by astronomy standards. Normally you have to go, the best you're ever going to do without TESS is maybe a day. So getting images every 30 minutes is just wildly good. And you're going to be taking these images constantly while TESS is rolling through these 13.5-day orbits. So you lose about a half day while it's closest to Earth, because otherwise you don't get the data sent down to Earth. And if all the awesome data is stuck on the spacecraft, that doesn't help anybody. But the idea is that you're pretty much constantly monitoring these sections that it's pointing at. And then the way it works through all the observations it's going to take is it'll stare at these points for 2 orbits. So 2 orbits takes about 27 days. And it'll stare at them for 2 orbits, move to the next one, move to the next one, move to the next one. And while it's doing that, there'll be a really nice section. You can see sort of this animation here. You can see there's a circle where it's basically always looking for one of these year-long observation sort of plan sequences. And that's really important, as I'll get to later, because if you can get exoplanets in there, you're going to be able to get a lot more transits. If you can get something like a supernova or the tidal disruption events I'm going to talk about later, it's really nice if you have a year's worth of data instead of just a month. But even when you get a month, you can do a lot of great science with it. So now TESS, like I said, its name is the Transiting Exoplanet Survey Satellite. Its primary mission is exoplanets, and it's great at that. NASA spent a lot of money to make it be good at that. A lot of really brilliant, really hardworking people are working on the mission to make sure that it's good at exoplanets. So it's been working for about 2.5 years now. It's found over 2,000 probable planet candidates, and it's been able to confirm, and subsequent follow-up observations have confirmed over 60 of these, nearly 70. There have been over, I think, near 10 or 12 press releases from NASA about the stuff TESS has been able to do in regard to planets. And all of this is great science. I don't want to, insult the exoplanet people. I do it as a joke sometimes with those that are my friends, but I think the better stuff that TESS does, I think its net science goals or its net science output is more from the non-exoplanet stuff. So I'm going to talk about mostly these 2 things. Basically, for me, the lens through which I look at TESS is that of extragalactic astronomy. So when TESS is looking for planets, it basically is restricted to what's in the Milky Way. It can only look at nearby stars because you have to have really, really high precision measurements of how bright those stars are when you see the planets going across. Because planets are tiny, they're not blocking out that much light. You need really, really good observations to study that. But if you're looking beyond that, you can sacrifice a little bit of that precision and still get really, really good science out. And when it's got those huge fields of view on the sky, you're able to see a ton of background galaxies around them at any given time. And when you do that, you're able to study things like supernova. These are exploding stars. I assume most of you listening have probably heard of those. And also things like tidal disruption events. And I'm a little disappointed that that's the name of these, because in undergrad, I got drawn to supernovae. It's this awesome name. It's an awesome event. And then tidal disruption events, it's such this clinical name for what is like a legitimately awesome phenomenon. Stars getting torn apart by black holes, and it has such a bland sounding name, which is too bad. But I'll get to those in a second. So before we get too far into supernova, I just want to mention what they are, in case anyone here doesn't really know or has only heard of them once or twice. So supernovae are stellar explosions. There's 2 pretty distinct types. There are some extras. Nobody at me. I don't think my research advisor's on here to yell at me about being too generalizing here. But so there's 2 kinds mainly. Core collapse supernova. These are probably what you've heard of if you've ever talked about supernova before. Basically, if you take a star larger than the sun, so 8 solar mass, significantly larger than the sun, so 8 solar masses, 9 solar masses, bigger than that. What's going to happen with them is they're able to fuse a ton of elements into their core, go all the way to iron. But the problem is, once you're fusing iron in your core, it requires energy. It doesn't produce energy to fuse iron. So once you do that, you're no longer generating the nuclear energy that sustained the star until that point. You're absorbing energy from the star, and what's going to happen is the outer envelope of the star is going to collapse down, you're going to bounce, and then you're going to get supernova out of that. That's what we call a core collapse. That's a big chunk of supernova, but it's not the one I'm going to focus on too much for TESS, just because it's not the one we've done that much TESS science with yet. Stay tuned. We're working on that. Hopefully it'll be out soon. But the one I want to focus on is what we call these thermonuclear supernovae. So if you take something like the sun, like a relatively low mass star like the sun, once it works through its life cycle, what's going to happen is it has a core of carbon and oxygen, but it's not heavy enough to force that material to be nuclearly processed beyond that. It requires just more pressure and more heat than the sun or a star of similar mass can provide. So what happens is you get a leftover white dwarf. Now, if that white dwarf is by itself, like what's going to happen with the sun, it's not going to really do anything. It's just going to cool for the trillions of years until the universe ends. But if you have that white dwarf has a companion of some sort, what can happen is you can get it to gain mass, and then it will explode as what we call a thermonuclear supernovae. Now, you might be wondering, why do we care about thermonuclear supernovae, these weird, what if the sun had a friend kind of events? The answer is, if you live on Earth, you probably should care. Basically, everything about the Earth, or really any rocky planet, has to come from one of these events. So you get this image I have on the left here is a periodic table, but colored by what kind of astrophysical source produces those elements. So if you care about having a rocky planet with an iron core and a silicate crust like the Earth, basically half of those elements are coming from these thermonuclear explosions, which is pretty important. I like living on Earth. I assume you like living on Earth. The other thing is that if you take a sort of a step back, and maybe an esoteric step back, and just ponder our place in the universe, our understanding of the universe, these thermonuclear, or type 1a, you might have heard them called supernovae, are how we know that dark energy exists at all. So these thermonuclear supernovae, basically because of the physics that drives them that I'm not going to get too far into, we have a really good understanding of how bright they are. And you can imagine, if I tell you have a 100-watt candle, and then you take that 100-watt candle and you stand 50 feet away, you stand 100 feet away, you stand 200 feet away, I'll be able to do some math from how bright that candle looks to me and be able to see how far away you are. Well, in the same sense, with these thermonuclear supernovae, we know how bright they are. If we look at galaxies that are further away, we can say, that was a thermonuclear, I know how bright it is. And then we can look at how fast that's moving away. And if we do that for a bunch of galaxies, we see that the entire universe is accelerating in its expansion. And if you follow that through with physics and some math, you find out that some 3/4 or so of the universe is what we call dark energy. It's this not really well understood, actually, I think it's fair to say not understood like at all, basically material or energy concept that is causing the universe to expand. But without these thermonuclear supernovae, we wouldn't have discovered, 3/4 of the universe's mass energy equivalents, which is pretty impressive. So, I say all this and you're probably thinking, oh, wow, we must have a really great understanding of these events, which would be a fair assumption on your part. And to some sense, it's sort of true. We understand that they're the nuclear burning of these white dwarfs. But how you actually get these white dwarfs to burn is not clear. So if you make a white dwarf by itself, it'll be on average, 0.6, 0.7 solar masses, which is nowhere near the limit. The limit where they'll go to these supernovae is about 1.4 solar masses. That's what we call the Chandrasekhar limit. So you have to find a way to build them to that if you're going to be able to invoke these in any significant number, and if you want to have a good understanding of them. And the general way we do that is we say, okay, so it's building towards this limit. It probably has a binary companion. Most stars have binary companions. It's a reasonable way to go about theoretically invoking that mass gain happening. And generally, we do two methods for doing that. Now, if you're ever going to read papers, they're generally called the single degenerate and double degenerate method, basically because it's a reference to the quantum mechanics that holds up these white dwarfs. Those names kind of suck. So for this, I'm going to call them single dwarf and double dwarf, just in reference to the number of white dwarfs that are in the progenitor mechanism we're invoking. So in a single dwarf system, you have your one white dwarf and it's nearby some like normal star. So something like the sun or a red giant. And what happens is it gets close enough that it siphons off mass from that star, builds towards a critical limit, that 1.4 solar mass Chandrasekhar limit I mentioned before. And if you have the correct mass loss rate happening onto that white dwarf, you can get it to build towards that mass and then explode as a supernova. There's a problem I get into later about there are reasons to doubt that. So people have been looking more and more into this double dwarf mechanism, where instead of having a white dwarf and a regular star, you just have two white dwarfs. And if you put them close enough together, you get gravitational wave loss. This is the same kind of mechanism that what LIGO is looking for out there near Baton Rouge, but on a much smaller scale than the two supermassive black holes. And while these two white dwarfs are orbiting, they'll lose some energy to that gravitational wave loss. And as they infall and merge, it's easy to understand the physics of why this might probably trigger an explosion and be seen as a type 1A or a thermonuclear supernova. Now, as far as the state of the field goes, there's not really consensus. It's not like people aren't obviously saying, oh, obviously it's the single dwarf mechanism, obviously it's this double dwarf mechanism. I've seen close to actual fights at conferences where people will be going to bat for one of these two scenarios. So you have the single dwarf guys come out and say, oh, it's obvious you could get one of these stars that evolves off the main sequence faster and goes through its life cycle quicker, and then you get the scenario set up. And maybe we haven't seen the predictions it makes, but it makes a lot more sense. The timescales work out better than the double dwarf, and then the double dwarf guys will come in and go to bat saying, look, you make all these predictions, we don't see them. How are you going to be defending this? I tend to fall more into the double dwarf camp, but there's still plenty of leeway for both. But in terms of the predictions, so I mentioned some predictions last slide. The idea is that, if you explode a supernova, you're ejecting over a solar mass's worth of material at 10,000 kilometers a second, and you're slamming them right into the star that's right there because it was feeding the white dwarf that then exploded. Like, there should be something that you're able to see from that. So, the first thing is that if you slam all this material into a star, you should strip off at least a little bit of that star, and this should be visible in the form of hydrogen or helium. So any star is going to have mostly hydrogen or helium outer envelope. That's just how most stars are going to work. So if you strip all this material and then you take spectra of the supernova later, you should be able to see this hydrogen or helium. And then the other idea is that at the same time that you're running all this high velocity ton of mass into the star, that should create a good bit of excess emission that you see as sort of a bump in the early time in the first half day, maybe day of the supernova light curve. And we've been looking for these for both of these signatures for quite a while because we really want to understand these type 1A or these thermonuclear supernova because, like I said earlier, they're really important for a lot of astronomy. And yet, as we've looked for them, we haven't seen these signatures very often. We've seen them rarely, but so I mentioned that it's not never, but it's rarely. So the first time we were able to see this swept up material, basically when you run into the star, you should strip off some of its outer envelope and it should be visible as hydrogen or helium, was just last year, actually. There's a paper out that said, aha, we looked at a pretty normal thermonuclear event. We saw this hydrogen emission feature that seems basically consistent. Like you look at this feature here, and it looks more or less like what we expected you would see if you had this single dwarf model happening. But with only one spectrum, there's some other things it could be. It could be that you just had hydrogen in that environment that you're running into that isn't exactly from a companion star. And so as Vera Rubin once said, the great astronomer, no observation problem will not be solved by more data. And in this particular case, we were fortunate enough to have TESS data. So when we went to the TESS data, we figured, okay, the hydrogen looks like a smoking gun for this single dwarf model. And if it's there, there'll be a nice little bump. It'll be easy to see. And yet when we go look there, there's not really obviously a bump. Basically you look at the residuals and it's just kind of as bumpy as it was before there was a supernova there at all. It just looks like the regular noise in the data. So it doesn't seem like there's anything there. We're able to rule out pretty much anything bigger than about the size of the sun, which is too bad because it would have been exciting to find like the smoking gun for, aha, these really can happen. That's where we're at. But, we're still going with TESS. The idea is going to be trying to find more of these as we go forward. TESS is a long-term mission, probably. It's unlikely that NASA is going to cancel it. So we're looking forward to that in the future. Now I want to spend the rest of I think I have like about 5 minutes left, talking about tidal disruption events. So for supernova, I have a whole spiel about how they're critically important to science, both cosmology and, the chemical evolution of the Earth and whatnot. With tidal disruption events, I don't really have that. They're too infrequent, really, to be critically important to most astronomy. But I've never really had a problem convincing people that it's just like really cool to see a star get torn apart by a black hole. So I'm just going to assume that that's working. I can't see anyone's faces, but I'm guessing y'all are pretty hyped about the idea of just, we watched a star get shredded by a black hole over like 6 months. So when this happens, what'll occur is that you get the star coming in, it'll get stretched out by the black hole, just kind of textbook tidal forces if you've ever taken an undergrad physics class, but it gets torn apart. About half of it will get thrown out into space, and the other half will end up in this accretion disk around the star. You can kind of think of, if you put water down the drain, that's the accretion disk of a black hole. And while it's interacting in that accretion disk is when it really brightens into what we see from Earth as the TDE, these tidal disruption events, but these can be really bright. They can rival supernova. They can outshine their galaxy. But like I mentioned, they're pretty uncommon. So supernova, there'll be one, maybe two every century in any Milky Way sized galaxy. Whereas these TDEs we expect closer to every 10,000 years you might see one. So when we did the math on what we expected to see with TESS while it was up there, we were kind of like, we might get one, maybe two faint TDEs while TESS is up there, just playing the odds. But luckily we got a much better outcome than that. So this is Assassin 19BT. This was, beyond all of our expectations. It was a TDE. It was extremely bright. We managed to find it right almost in the center of the continuous viewing zone. So just a reminder, that was that region of space that TESS is always looking at during a year. So we have pretty much a year's worth of data looking at this, and about halfway through it, this TDE just pops up, and you go through, it can't be just an active galactic nuclei. It can't be the supermassive black hole at the center of the galaxy that's just always eating because it wasn't doing stuff before. It has to be a TDE. You go through the spectral analysis that works out. And this is just unprecedented observations of a TDE. You never get to see them this early. You never get to see them this continuously. We've got obtained all kinds of new constraints on TDE theory because of this. All the models we had before were just sort of, you would see them maybe as they hit peak, and then you'd be able to say, okay, let's study this decay over here. But having access to this rise as it was happening was just incredible. And then here I kind of want to make the point of expectations versus reality on these things. So if you may have heard about this, I know TESS or that NASA ran a bit of a press release, but press release versus real data is always a sad reality as an astronomer. So you can see on the left here is a very believable model from James Guillaume about what these TDEs actually look like. And then on the right is what it looked like in our data. So, and on the left with the simulation, you have these beautiful structures in the disrupted stellar material. And then on the right, it's so far away that you can't resolve it. And it's 4 pixels brightening. And that's the challenge of all of this adventure, is dealing with those 4 pixels and trying to do science with what is a limited window into the physics of the whole adventure. And then I think I'm allowed to say this. No one's here to yell at me, so, I'm going to do it anyway. We submitted this like a week ago to a journal. We probably found, I'll go that confident, second TDE in TESS. This is called Assassin 14KO. So back in 2014, when Assassin, the supernova survey I work on here at LSU, first ramped up. First was getting its ability to take an image of the whole sky every night. We found what we thought was just a typical core collapse supernova. You took a spectrum of it. There was hydrogen. It looked like what we thought these core collapse events look like. However, recently, Anna Payne, a grad student at Hawaii who works on Assassin, was looking through some of our data and realized this peaked every 114 days. And core collapse events just can't do that. If you lit off a core collapse event, all that's left is this neutron star or black hole. There's no way to get it to look like another core collapse anyway, with what can be left from that compact object. So you go through and you're like, no, this is, you see here, these are pictures or images of the light curve, basically how bright the thing was. Near that 114 day mark for the next, 6 years, we've been able to see it every time it comes up to the similar brightness. It's definitely there, it's definitely real, which is very interesting and weird. And we lucked into the fact that TESS was able to see it again, this one as well. And when you look at this TESS data, you compare it to Assassin 19BT, the decay after you make some corrections, just scrunch it down a little bit, looks almost exactly like 19BT. It's very smooth, seems very likely to be another TDE. And it's also very interesting that it's a partial TDE, because if you took apart the whole star whenever you came in on orbit, you couldn't get it to repeat every 100 days or 114 days. But if you have it, basically the star gets a little close, but not so close that it's totally torn apart. You tear off a little bit of it, that forms an accretion disk, it brightens up as a TDE, and the star goes around and comes back, and it does that every 114 days. You can get a repeating TDE, which is very interesting, and again, I don't think has ever been seen. So it's really cool stuff. I'm very excited about it, but we're awaiting peer review on that, so nobody yell at me if I wasn't supposed to say that yet. So just in conclusion, I think TESS is great. I rib my exoplanet friends about how TESS is not really an exoplanet mission, but it is great for that. It does awesome science in the exoplanet regard, but it does a lot more than that. I've talked about the exoplanet or the extragalactic transients here, but there could be, I could give an entire talk, or someone who's more than me could give an entire talk about how TESS is used is studying the solar system. It does great asteroid tracking. If you train it on that, it can do minor planets. It does awesome work on stars and also AGN. But in any case, I'll just leave up this fun video and let Courtney feed me any questions that there might be.
Yes, hello. You post these kind of GIFs all over Twitter, and they're great there and they're great here. But I do have the honor of the first question. I'm actually going to take the first two questions because the first one is not a real question. But I want to know how you feel about Ohio State losing Joe Burrow to LSU.
I'm okay with that. I'm not that mad about that one. I like Joe. I'm cool. I had a good time rooting for him against Clemson. I can't be mad because I got to watch Dwayne Haskins and Justin Fields for the last 2 years. I'm a little processing my emotions about not having Ohio State football in the next month, but I'll live.
All right, and my real question is a very simple question. What is your favorite type of supernova? I know there's like 6 or something like that. What's your favorite?
I think my favorite is Type 1A. It's a little rough because I feel like they're way more important, but that's really tough, man. Core collapse are more fun to study, but I feel like I like Type 1As more.
All right. Well, we've got quite a few questions, so I'm going to start from the top. Patrick Fasano wants to know what the real name of Assassin 18TB is. You might mean 19BT, but I don't know if you mentioned the other one.
Oh, I think Patrick is giving me crap.
Oh, okay.
So the TESS, basically with supernova, the way they work is every survey that finds them will give them their own internal name. And then there's also you report them to the IAU, the International Astronomical Union. They'll have some designation that they assign. I think the IAU name, which I'm assuming is what Patrick is fishing for, is 2018 FHW for Assassin 18TB. And if I'm right, I deserve a cookie because those are hard to remember. That's part of why I prefer the survey names, is because the survey names only ever have most of them only ever have 2 letters, so they're a lot easier than the TNS names that are really long.
Yeah, that's like I study variable stars, and I much prefer the ones that have humanish names, like XXCam, as opposed to the 2 mass phone numbers.
Exactly.
But our next question, Susan Dorsher asks, how much of accretion disk physics around white dwarfs is dominated by frame dragging in relativity? Is the light trapped and magnified as well?
That's a great. I want to say not that much, but I am definitely not an expert on it. So it's more nova physics, I think, than white dwarfs. Or than thermonuclear, because thermonuclear supernovae, by the time they get triggered, the accretion disk around the potential white dwarf, the accretion disk around the white dwarf doesn't matter pretty quickly. You've expanded beyond that within maybe an hour. But I want to say not that much for supernovae, but a ton for novae. But someone's going to quote me on this and drag me, and I'll probably deserve it.
All right. Patrick also asks, why a repeated TDE rather than a recurrent nova?
So for Assassin 14 KO, it's almost certainly not in the sky. So we look at the distances of it. We did some sandy checks to make sure, but if it's extragalactic, a recurrent nova wouldn't be bright enough to be what Assassin 14 KO is doing. And also, I don't think recurrent novae usually happen on quite that short of a time scale. They're usually longer, but mostly the distance calculations don't back that up.
All right. Susan also has another question. She says, if I remember right, supernovae are beamed along the poles to some extent. I've heard that the beaming is synchrotron in magnetic fields. Do general relativistic gravitational effects also amplify that?
I think that's more of a problem, a potential concern for core clouds, but I think it's, again, something where the bulk of the ejecta ends up not really being a synchrotron emission kind of issue, except for if you have the kind of hypernovae that lead to GRBs. So it's a special brand of supernova, what we call the type 1c broad lines, are associated with these gamma ray bursts. So if you have gamma ray emissions, they'll see a ton of emission occasionally, and these seem to be tied to a specific type of supernova that's tied to a specific type of high mass star going off. And those, I think, have significant relativistic contribution to the emission. But the others, what I was talking about when I meant core collapse here, is pretty standard high mass. These are called type 2 for those who follow high-end astronomy stuff. but those are going to be not that relativistically driven, at least as far as the emission is. You could model as just punching a bunch of energy into the center of a high mass star and seeing what happens, which will not be overly relativistic.
Okay. While I wait for another question, I have some more that I can ask you. What was it like when you found the TDE? Did you have to like teach yourself basically how TDEs work super fast, or did you have more help?
That was a fun, yeah. So I had a lot of help. The first author on that is named Tom Holloy, and he's been doing, so Assassin has found some TDEs before. So he'd had a bit of help, a good bit of experience on those. And he was able to walk me through a lot of what we were seeing. And I mean, he was the first author on the paper, so he did a lot of the analysis. But it was pretty exciting to me because I in my undergrad, I'd studied supernova. And once I got here, I started studying supernova. And then I got called in because I was the guy doing test stuff to try to help study this TDE. And I'm like, oh, I don't really know anything about these other than the name. So that was a really fun time. I kind of enjoyed, getting to learn a lot.
Cool. I think that is all of the questions we have. I was originally going to bring Matt back, but I think he's answered most of the questions in the chat, so I'm going to sort of leave that where it lies. If you have more questions for Patrick, you can probably shoot them straight to his Twitter, and he will probably answer them for you. But with that, that's going to be everything we have for today. It was, kind of a short show, but we tried to keep it, simple so that we didn't have all the moving parts as we normally do at a normal AOT. But thank you everyone for coming. Please let us know in the chat or on our event page what you thought of our event. We'd love to hear your feedback. We will have another show next month, is TBD who the speakers are or when it will be. But we will continue to be virtual until further notice, as long as, I mean, it seemed to work pretty well. I didn't see any hiccups in the stream, so we look pretty good for now. And so we'll stay here like this for now. And I want to go ahead and give a shout out to our staff that's working behind the scenes. You can't see them here, but they are there. That would be Allie, Tyler, and Alex. They're on campus at LSU, running the stream, putting everything on Facebook, moderating the chat. Maybe she's going to show her face. And when you're doing our, when you're donating to Venmo or PayPal, if you don't know which BattleBot to choose, you can see our lovely image on our Facebook, Twitter, or Instagram. Allie worked really hard on those, so you should certainly look at them because they are amazing and hilarious. But until next time, everybody stay safe, stay curious, and we'll see you around. Bye, everyone.